Okay. Hello everyone. So this is Ravi Teja Vemulapalli. I'm a research scientist and manager in the machine learning research group at Apple. So today I'm going to present some of our recent works focusing on addressing data scarcity by leveraging foundation models, data retrieval, and data synthesis techniques. Before I get into the details of the talk, I would like to thank all my research collaborators who contributed to the work that I'm going to present today. Throughout this talk, I'm going to focus on a particular problem setting, which is probably a fairly standard setting that many of you would be working on, which is we are interested in training a neural network of particular architecture for a particular target task we have in mind. And the problem is that we have only limited label data for this target task. And we want to do our best in training our network so that it performs very well for this task. So this is the standard problem setting, which will be the focus of this talk. And I will be presenting two of our recent works in this talk that address data scarcity. The first piece of work, which will be the main focus for this task, is our recent ICML paper, which focuses on leveraging foundation models and data retrieval techniques to address the problem of data scarcity. Most of the experimental results I'll present for this work are not on data sets related to industrial inspection domain. However, the goal of presenting this work here is to encourage this community to explore these approaches for problems that you may face in the domain of industrial inspection. And towards the end, I'll briefly talk about an ongoing work that focuses on particularly the manufacturing defect segmentation problem, where we try to leverage synthetic data to address the issue of data scarcity. Okay, let's dive into the first topic, which focuses on leveraging vision foundation models to address the situations where we don't have a lot of data. As I said, the focus is on this setting where we are interested in a particular target model and we only have access to limited data from this particular target task. Typically, when we don't have a lot of data, a fairly common paradigm that everyone follows is transfer learning, where we'll first pre-train our model on a different data set, which we often call as pre-training data set, which is often large, but is not directly related to our target task. And then after pre-training the model, we use those weights to initialize our target model and then fine-tune it on the small labeled target data set that we have. This is, I guess, more or less a standard strategy that many of you would be adopting in your problems. There are various popular pre-training strategies that are out there in the literature. Two most common ones that many of you might be using is either supervised ImageNet pre-training, where we'll pre-train our network using labeled ImageNet dataset, which has more than 1 million images labeled with 1,000 different object categories. Other popular pre-training strategy is self-supervised pre-training, where the model is trained on large scale of unlabeled data sets using a wide variety of self-supervised loss functions that have been proposed in the literature over the past decade. More recently, another pre-training approach has gained popularity, which is CLIP, which stands for Contrastive Language Image Pre-training. This approach uses paired image and text data sets to pre-train a model. Specifically, it has an image encoder and a text encoder, and then the model is trained such that the representations of image branch and the text branch match with each other. This has gained a lot of popularity over the last couple of years as it has been shown to be an effective pre-training strategy, specifically in the setting of large models. Let's see how these popular pre-training strategies perform when we evaluate them onto target tasks. Here, the left figure shows results on an image classification task where we use a satellite image dataset as our target dataset. On the right, we show results for semantic segmentation task where we use ADE20K dataset, which is a popular semantic segmentation dataset. And the model that we are training here is a fast VIT encoder model. And for classification tasks, we use a linear classifier with this encoder model, whereas for segmentation tasks, we use DeepLab V3 decoder. And for pre-training this model, for CLIP pre-training, we use a large data set consisting of almost 700 million image text pairs, whereas for self-supervised pre-training, we follow the Dino SSL approach and we pre-train it using around 3 million images on CC 3 million dataset. And then we fine tune these models on our target datasets and see how they perform. As we can see here, among these three popular or widely used pre-training strategies, ImageNet pre-training performs the best. And probably this is one of the strategies that many of you already use in your works. Now, is that the best we can do? There are these popular vision foundation models that are available these days. And the topic of this work is, can we use these foundation models and do a better job at pre-training the models that we are interested in training? What are vision foundation models? Typically, these are pretty large models, and they're trained in a self-supervised fashion and massive, really large-scale image or image text datasets. And these models are very popular because they have been shown to work well on many downstream tasks, and also they have been shown that we can easily adapt them to new tasks with limited label data. However, these models, just because they're too big, they may not be easily deployable in many practical settings because of the high computational cost and high inference latency. However, we might be able to use these models to pre-train the small models that we typically deploy. Let's think, how can we actually leverage them? Probably one of the first things that would come to our mind is to pre-train our models by simply doing representation distillation, which is a standard knowledge distillation framework, where we can take the foundation model, run it on a large data set of unlabeled images, extract feature representations, and then train our target model by saying that the target model should produce same feature representations as extracted by the foundation model, a standard knowledge distillation framework. And we can train our model like this. Note that this is a task agnostic way of transferring knowledge from the foundation model to the target model, because the notion of our target task has not been used here. The foundation model was not trained for our particular target task. So this is like a task agnostic way of transferring knowledge. Let's see whether this way of leveraging foundation models is effective. Will it give us better models in the end? Looks like the answer is not clear. For example, if we evaluate this strategy on Eurosat classification task, it doesn't seem like it is outperforming ImageNet. Whereas if you look at on semantic segmentation in the ADE20K dataset, it does outperform ImageNet pre-training. So overall, it is unclear if this is definitely a better pre-training strategy. And here, in order to train this model, the knowledge transfer dataset that we have used is a generic web dataset with about 3 million images. And the foundation model that we have used in this case is Dino V2 VIT large model. So the first set of experiments didn't give us promising results. Looks like maybe these VFMs are not really helping us that much. However, the right question to ask is this task agnostic way of transferring knowledge the most effective way to leverage these VFMs? The answer turns out to be no. A better way to leverage them is to follow a task-oriented knowledge transfer strategy. By task-oriented, we mean let's first teach our task to these foundation models. We have small amount of label data for our task, and the foundation models are supposed to learn new tasks with small amounts of data, so we can teach our target task to these foundation models. And then once we have a fine-tuned foundation model which can do our particular target task, then we can do knowledge distillation. We can train our target network by distilling from the foundation model, and instead of matching representations, we can directly match the target predictions because the foundation model now knows how to do our particular task. So this is a task-oriented way to leverage foundation models and transfers knowledge from foundation model to a target model. Let's see how this way of leveraging foundation models performs. So here is a comparison between ImageNet pre-training, which was the best one among the standard approaches, and then task agnostic way of leveraging foundation models, and then task oriented way of leveraging foundation models. Again, the experimental setting is the same as the fast VIT target model, Dino VIT foundation model, and then the transfer set that is used to transfer knowledge is the generic web data. The same web data set CC3M is used for both task oriented and task agnostic knowledge transfer. As we can see, task oriented transfer clearly outperforms, both ImageNet pre-training and task agnostic pre-training. So the summary so far is there are numerous ways to pre-train the model that you are trying to pre-train for the particular target task you are interested in, such as ImageNet pre-training, Dyno pre-training, Clip pre-training, or you can leverage foundation models in two different ways, either doing task agnostic knowledge transfer or task oriented or task specific knowledge transfer. And among all these, leveraging foundation models via task oriented transfer is the best approach. And as I said, in all these experiments, we have used a generic web data set consisting of 3 million images, which is CC3M, as the knowledge transfer set. But is that the best data set for knowledge transfer? Or is there a way we can find better transfer sets for making this knowledge transfer more effective? That's the next natural question to ask in this context. And one potential way to curate better knowledge transfer sets is image retrieval. So as I said, we have small amount of target data with us. So we can use this small amount of target data and perform image retrieval, where we will use a large data set as a gallery and retrieve images that look similar to our target data set. For retrieval, we can use embeddings that are extracted by some pre-trained clip model, like a large open clip based VITL model, and it gives us image embeddings, and using these embeddings, we can perform image retrieval. And these days, there are pretty large scale data sets consisting of billions and billions of images like Lion or Datacomp, which we can use as gallery. Or if you are working on specialized domains, if you have access to large scale data sets, unlabeled data sets in that domain, you could use those as the gallery and then retrieve images that look visually similar to the target data set that we have. This way, basically, we are expanding our target data set to create a large scale unlabeled data which consists of images that look like target images, and then we will use them for knowledge transfer between foundation model and target model. Here are some basic retrieval results to demonstrate how retrieval based on clip embeddings works. So here the query images is ADE 20K data set, and we used a data set which consists of 15 million images, which is YFCC 15M, as our gallery. As we can see, using clip based retrieval, we can find images that look similar to our query image. And this is a very simple, straightforward retrieval strategy. Now the question is, these images which we have retrieved, how well do they actually perform if we are using them for knowledge transfer? Let's look at the performance numbers on the ADE 20K data set. So the setting here is that we have ADE 20K data set, which is like a small amount of labeled data that we have. And then we use it as a seed data set and then expand it by retrieving images from YFCC, and we curate a data set which consists of around 150,000 images. And then we compare whether this curated data set with 150,000 images and a CC3M data set which consists of 3 million images, which is a good data set for knowledge transfer. And as we can see here, the curated data set is better than CC3M, even though it is significantly smaller in terms of the number of images. This basically shows that by using retrieval, we can curate good data sets fairly easily. And even though they are smaller in terms of the number of images, they may be more effective than generic web data sets we may get for knowledge transfer. Now, this type of image retrieval, which looks fairly simple, which is like you extract image embeddings and then do retrieval, it may work well for many of the common data sets that people may work with. But if you are working with some specialized domains or stuff, outright they may not work very well, because maybe the visual patterns that you are looking for, the patterns that you observe in your target data set, may be embedded in subregions of images that you have as gallery. For example, I'll show a few examples later. Let's say here, where in this setting, for example, we use Eurosat dataset, which is a satellite image dataset as query, and then we use Datacomp dataset as our data set. Focus only on the left images and the right images in this here, whereas the left column and right column, the left column images and the right column images, if you observe, you can notice that maybe the left column images are like sub-regions in the right column images. That's what I mean, where sometimes your gallery might consist of images which may not exactly look like your target, but if you go inside and search for sub-regions, you may find the right matches. So that is one way you can do retrieval. It's more like a fine-grained retrieval to actually find relevant images. So we do adapt that strategy in this work. So we call this augmented crop retrieval. So what we do is you have a large gallery you obtain in the beginning. Instead of directly searching in the gallery, let's just first expand this gallery by randomly creating crops out of these images and also augment these crops using photometric and geometric augmentations. This way, you can create a much larger expanded gallery with increased diversity of the visual patterns that you can find, and then we actually go and search in that expanded gallery. Again, we will use the same clip embeddings to search, but the key thing is that we now have a much bigger gallery which has more smaller image regions in it. And now let's go back to this figure where in these experiments, as I said, we started with Datacom data set, which consists of 1 billion images as a gallery, actually 1.28 billion images. And then we expanded it by 10x by creating 10 random crops for each image in the gallery and then adding various photometric and geometric augmentations. And then we obtained a data set which consists of 12.8 billion augmented image crops, which is referred to as Datacom DR here. And then we go and search for this satellite image type images in this gallery. As you can see here, the middle column in each of these figures shows the matched crop, which does look like the query, but the right column shows the actual original image in the Datacom dataset. So basically, we identified those correct subregions by going and searching through the augmented crops. If somebody is interested in exploring this dataset for any of their works, this dataset, which has this 12.8 billion crops, is available publicly. This QR code will take you to the Hugging Face website where the dataset is shared. I want to highlight this particular point, which I mentioned already. When we do this type of search, going through subregions of images, we may find patterns that look like our target data sets, even in images that are completely unrelated to our target domain. For example, here, the query is like a satellite view of a river, and the image crop that we obtained, which is shown in the middle, does look like an image of a river from satellite view or a sky view. However, actually that particular image was obtained by cropping the red rectangular box in the right image, and the right image has nothing to do with satellites, nothing to do with rivers. It's just an image of some army division Boolean. And if you just crop that rectangular region and add some photometric augmentations, it will suddenly look like a river image. So this is like a way you can find visual patterns, even though the actual gallery is totally unrelated or fairly far away from your target domain. So that's effectively what we did here. Let's see if the data sets that you curate like this are effective for knowledge transfer. Again, here we are showing results on the satellite image classification dataset, where we compare pre-training this fast VIT model by doing knowledge transfer from the open clip model, VIT model as the VFM. The comparison here is between two different data sets which are used for transferring the knowledge. One is the generic web data set, which is CC3M, which consists of about 3 million images. And the other is a small data set which consists of just 50,000 images, which was curated by doing this crop retrieval. And again, as we can see, the curated data set performs much better than the CC3M data set. Overall, there are two things that I covered so far. One is transferring knowledge from vision foundation models by using task-oriented knowledge transfer strategy. Then the other is creating effective data sets for actually transferring this knowledge. By putting these two things together, task-oriented knowledge transfer with data sets that have been specifically curated using image retrieval, we can get in the end significant performance boost, especially when the amount of target label data that you have is fairly limited, as we can clearly see here. And we also get, if we look in terms of data reduction, we see that we can maintain performance by reducing the amount of label data that is needed for both these tasks. So to conclude this part of the talk, overall, the key message here is whenever we are training a model for a task where we don't have a lot of data, we often end up pre-training it. And there are numerous approaches to pre-train your models, like ImageNet, Clip, Dino SSL, which are fairly standard approaches. Or you can even leverage foundation models and then do knowledge transfer. And when you're leveraging foundation models, the best way is to do task-oriented knowledge transfer. And the best data set to transfer is something that you can curate using image retrieval or image crop retrieval. Okay, I'll now jump into in the remaining time. I'll briefly talk about an ongoing work where we specifically focus on defect segmentation in the manufacturing setting. And the focus of this work is to leverage synthetic data to address the problem of data scarcity. As all of us know, collecting large-scale annotated data sets for defect segmentation is tough. Defects are rare, and then manually annotating the defect regions is time-consuming and costly. This is a standard problem that everybody faces who is working in the manufacturing domain. In this work, we address this data scarcity problem by using synthetic data. And to generate synthetic defect data, we use a cut and paste framework, which I think is quite popular or well known in this community. It's a fairly standard framework where we have access to small training data set of defects. So we cut those defects from this and create defect instances. And then we can augment these defect instances using various photometric and geometric augmentations, and then create more defect instances. And then we can paste these defect instances on clean background images by eventually creating synthetic images with defective products. And then we can use this synthetic data to train our defect segmentation network. This is the standard cut and paste framework. The key question to answer in this context is, where should we paste these augmented defects? Of course, we can create a lot of augmented defect instances, and we can paste anywhere in a clean background image, but is pasting everywhere meaningful, or are there actually more important locations or more effective locations for pasting this defect so that the synthetic data we generate is more effective? So we try to answer this question in this work. To answer that, what we do is we introduce a neural network in this data generation pipeline, which is referred to as location prediction network. The whole job of this network is to take a clean background image and then predict a heat map. The heat maps is used to decide where should we paste defects to create synthetic defect data. So this pasting location heat map is the key part that we are going to learn in this data generation network. So this is a learnable neural network, and we want to learn this network by training. So effectively, we have two networks now in our setting where there is an actual segmentation network which is doing the job of defect segmentation, and that network is trained with synthetic data. But to generate the synthetic data, we need to know the locations to paste these defects and in our cut paste framework, and those locations are kind of predicted by this location prediction network, which is part of the synthetic data generation pipeline. We train both of these networks together using a bi-level optimization framework. So the goal of this framework, or the objective of this optimization problem, is to maximize the performance or minimize the loss of the segmentation network on a held out real validation data set, while the network itself is trained only on synthetic data that is generated using the location prediction network and the synthesis generation pipeline. I won't go into too many details here, because if you are interested, you can find the details more in the paper, which will be on archive soon. It is not yet, but in a few days it will be on archive. So I'll present some preliminary results here that we got on Emitech data set. So the goal here is, as I said, there is a network which is learning how to identify the important locations to paste defects, and then effectively generating synthetic data, which is used to train the segmentation network. So and the comparison here is pasting these defects at random locations on the background images, or pasting based on the heat maps learned by the network. As you can see, the learned locations perform much better, which means they basically give us more higher quality synthetic data, which eventually helps to train the network much better and results in final segmentation performance, which is significantly better. And the bottom figure here shows the evolution of the heat map generated by the network. In the beginning, the network is randomly initialized. It doesn't know much, so the heat map is all over. So it just thinks everything is equally good. But as we keep learning, the network kind of converges to identify the product foreground region, because if you are interested in detecting defects on these products, we should create synthetic data by pasting on those product regions. And the network automatically learns this without any explicit supervision. We really don't have any supervision of where the product is in the image, or which is the effectively the important region. So the network learns this automatically, because we are optimizing in the end to get the best training data set, which eventually leads to best final segmentation performance. I'll conclude my talk with this. So if you have any further questions, please reach out to us, or please refer to the papers. Thank you.